Here's a script with 3 different ideas from week 5, the first of which is going to be the notion that there are 2 different ways of specifying subsets of a given set, and they lead to equivalent versions of the proof that for any set, the power set is larger in cardinality than the set itself. I'm going to stick with the cardinality of 10 so that things fit nicely on the screen. And now that I have selected 10 true and false values and displayed them, I can show you an alternative way of doing this. The R function which just lists the positions in this list for which the value is true rather than false. 1, 2, 3, 7, and 9. So let's now choose 10 subsets and put them in a list and print them out. There we have 10 random sequences of true and false. And using the Cantor diagonal approach, which I trust is familiar to you, what I'm going to do is first to extract all the diagonal elements. I've created an empty logical vector to hold them, and then I'm just going to keep concatenating the ith element from the ith sequence in the list. And then I'm going to reverse all the truth values. So here is a vector x that cannot possibly appear on the list. If I display the entire list with x below it, you can see why not. Because x has a true in the first position, but the first vector has a false in the first position. X has a false in the second position, where the second vector has a true. In the third position of x, we've got true. In the third position of vector 3, we've got false. This is thoroughly uninteresting when the set is finite, but when the set is countably infinite, the proof still works. Now let's do the same construction, but we'll use the second approach for representing the sets. Namely, what we will do is get the positions for which we have a true in the ith sequence on the list. And now, instead of 10 vectors of true and false, we have 10 subsets of the numbers 1 through 10. But the content is exactly the same, and exactly the same construction will work. People find this much more mystifying than Cantor's version of the diagonal construction, but it's exactly the same. I create an empty numeric vector, and then I ask, is element I, the index 1 through 10 of the set, an element of the ith set on the list? And if it's not, I concatenate that index with the initially empty vector xx. Let's see what happens. There it is. This is a vector that cannot appear on the list, and you have to remember this now. 1, 3, 5, 6. Okay. 1 is not an element of set 1. 2 is not in the set 1, 3, 5, 6 because 2 is in the second vector. 3, however, is not an element of itself, and therefore this set 1, 3, 5, 6 cannot appear anywhere on the list. Okay, let's move on to quite a different topic now. Namely, what happens if we try to graph discrete or mixed discrete and continuous distribution functions? For a discrete distribution, like the binomial distribution, I prefer the name mass function to density function. On the other hand, R uses the prefix D, so let's stick with that. And you'll notice that the binomial distribution for n trials with a probability of 7.5 has the probability for the value 3, which is equal to the number of ways of choosing 3 elements from a set of 7 divided by 2 to the 7th power. If I ask dbinom what's the probability of 3.5, it will tell me 0, because you gave me a non-integer x, although it does give me back a value 0, which indicates the probability of that event is 0. So, for a discrete distribution, the mass function is arguably just barely defined for non-integer x, but it's not meaningful. The distribution function, however, makes perfectly good sense. If I ask for p-binom, that's the probability that in 7 trials with a 50% probability of success, I get 3 or fewer successes. It says the answer is 0.5. If I ask the same question for 3.5, it says the answer is also 1.5. You can't get anything more added on until you get up to 4. If I ask it, what's the value of p-binom for -1, it tells me 0. The probability of being less than or equal to -1 is indeed 0, and the probability of being less than or equal to 10 is 1. I can plot this distribution function perfectly nicely, and when I do that, I see I get a sort of staircase effect. Notice in doing curve, I gave it n equals 1,000, which is more points than it usually likes to plot. That makes the discontinuities a bit easier to see. Now, with some effort, I can mix a discrete function and a continuous function. So here is a probability distribution function. It's a function of x, and this has the constant value. Let me plot it first. This has the constant value 0.2 when x is greater than 0 and x is less than or equal to 1. I take x to the 2/5 and multiply that by something which is equal to 1 only when x is greater than 1 and less than or equal to 2. I can do 0.8 for x between 2 and 3, 1 for x greater than 3, and I have this nice function which has a finite probability for the values 0.2 and 0.8, but also achieves any value in between 1 and 2. The only requirement on this function is that it has to be increasing. Start out at 0, end up at 1, and you'll see the only points of discontinuity are the ones for values that have a non-zero probability. Now, you will recall there are 2 ways of computing an expectation of a random variable. One is to multiply the density function by x, and in this case, what I'm going to do is say the only part of this that's continuous is the part from 1 to 2, so I will integrate this restricted density function from 1 to 2, take the value of that integral, and then add on 0.6, reflecting the fact that I have a 0.2 probability for x equals 0 and a 0.0 probability for x equals 3, which contributes 0.6. Notice that was kind of messy. I had to deal separately with the discrete part and the continuous part. A clever approach is to use the tail integral theorem. So I'll define a new function called tail. That's just 1 minus capital F, the probability that the random variable x has a value greater than x. Here's a plot of that. It is never obvious to me that integrating this function from 0 to infinity is going to give me the expectation, but it does. I only have to integrate up to 3 because beyond that point the value is 0, and I get the same correct answer, 1.533. Let's move on to our third topic, namely doing dyadic integration in 2 dimensions. And what I'm going to do is integrate the function x squared plus y squared over the unit circle. If you're a physicist, you will recognize that as what you would do if you wanted to calculate the moment of inertia of a uniform disk. The correct answer is pi over 2. To do it dyadically, we use 4 unit squares from -1 to +1 in x, from -1 to +1 in y. We subdivide them, and we define the indicator function of a function f that is 1 inside the unit circle, that is x squared plus y squared inside the unit circle, but 0 outside the unit circle. Now I can integrate this over the square that runs in both directions from -1 to 1, and I should get close to the correct answer. If, as my level of dyadic subdivision, I choose to use only 2, then I wouldn't expect to do notably well. Why? Because I chose a sequence of only 8 values for x, 8 values for y. That means we've got 64 squares, and what I'm doing is counting 1 for squares that intersect the unit circle, 0 for squares that don't. There are my 64 pairs of xy values. I take the sum of my function f evaluated over those and multiply by the square of 2 to the minus n. That's the area of a dyadic square, and I get the value 1.66. That's a little bit bigger than pi over 2. Now I'll repeat this with a higher level of dyadic subdivision, namely 8. Now I actually have a very large number of values in each dimension, 512. So dyadics is a vector of length 65,536, but that doesn't bother R. And when I do the Riemann sum, I get 1.570866, which is very, very close to pi over 2. So that's one way of doing this. It's not exact. If I want to do it exactly, I can use Fubini's theorem. If we do Fubini's theorem, what we have to do is choose the limits of integration to lie on the boundary of the circle. So here's the function of x and y that I'm integrating, and I'm going to show you how to do the integral over x for y equals the square root of 3 over 2. It took me a while in reading the documentation to discover that ... meant additional arguments to be passed to f. In the past, I've told you you can only integrate functions of one variable. That's not quite true. By specifying values of all but one of the variables, you can get the integral over the other. And here, if y equals root 3 over 2, I have to integrate from x equals -1/2 to +1/2. And it works. Now that I know it works, I can do it for all values of y. So now I'm going to define a function of y that results from integration over x with the correct values for the limit of y that I substitute in. Now I have a function of just one variable. It turns out it doesn't get born in vectorized form, but if I put capital vectorize in front of it, then R will be very happy to integrate it from -1 to 1, and I get exactly pi over 2. Which means that if you want to use Fubini's theorem but don't know all the antiderivatives that you need, you can still get R to crank out the right value numerically for you. Well, I ran 3 seconds over the limit, so I'm going to be warned that this may be too long for YouTube, but I know better. It'll be there in a few minutes.